Imagine walking into a dense forest at midnight. Without a moon or artificial light, the environment provides almost no visual data for the human brain. Your biology attempts to adapt. Your pupils widen to their limit, and the rod cells in your retinas, specialized for low light detection, strain to find enough photons to construct an image. In this environment, human anatomy reaches its functional end. Without enough light to trigger the necessary chemical reactions in the eye, you are effectively blind. Sliding a pair of night vision goggles over your eyes reveals a world that was hidden just seconds ago. The landscape is suddenly defined by sharp edges, distinct terrain, and figures visible from dozens of meters away. These goggles operate by capturing and magnifying the faint illumination already present in the environment. Most nighttime environments contain ambient light from starlight, distant urban centers, or light scattered within the atmosphere. The goggles also detect near-infrared wavelengths, a spectrum of light that bounces off objects just beyond the range of human perception. Environments that appear empty to the human eye actually contain a constant stream of light particles available for electronic collection. To see how this works, we must look past the rugged casing of the device and follow the path of a single light particle. This photon bounces off an object in the dark and travels toward the goggles. The objective lens at the front of the device gathers this weak light and focuses it, acting much like a funnel to concentrate the signal. That focused light hits the photocathode, a specialized layer serving as the first transformation point. When the photon strikes, the photoelectric effect occurs. The material absorbs the light's energy and ejects a single electron into the vacuum behind it. At this stage, the information has changed form. The physical signal of light has been converted into a measurable electrical charge. Because the light in a dark forest is so sparse, the photocathode only releases a small number of electrons. This signal is too weak to create a usable image. To increase signal strength, electrons enter a microchannel plate, a disc of microscopic glass tubes. As an electron strikes the sidewall, the collision knocks two more loose. They strike again, creating 4, then 8 in a chain reaction, multiplying into thousands. This process bridges the gap between the invisible and the visible, turning a faint electrical signal into a dense, high-energy stream of data. This stream of electrons exits the microchannel plate and strikes a phosphor screen at the rear of the vacuum tube. The impact of the electrons causes the phosphor to emit new photons, effectively converting the electrical signal back into visible light. An ocular lens then magnifies this light and focuses the intensified image for the user's eye to see. Outside of this microscopic process is the physical housing, which keeps the lenses and the high-voltage vacuum tube in precise alignment. Night vision is the result of mechanical alignment between optics and quantum-level electronics built to survive the extreme conditions of the field. Traditional phosphor screens glow green, while many modern systems use white phosphor tubes to create a bluish-gray image. These colors are a specific choice for human perception. The human eye is highly sensitive to variations in contrast and detail within these specific light frequencies. The goggles do not show the actual colors of the nighttime environment. The brain perceives a processed representation of amplified brightness data to maximize situational awareness. There is a scenario where this technology reaches its limit. If a user enters a completely sealed underground room with no external light sources, the system fails. Image intensification requires reflected light to function. In a space with 0 photons, the multiplier has nothing to work with, and the display remains dark. When there is no light left to amplify, a different approach to physics is required to see in the dark. Every object with a temperature above absolute zero constantly emits energy in the form of thermal radiation. To see through total darkness, the focus must shift from searching for reflected light to detecting the heat emitted by the environment itself. Which leads to that familiar, eerie green glow. In popular culture, this image is treated as if the device is magically lighting up the dark. But if an environment has 0 visible or near-infrared light, an image intensifier has nothing to amplify. It is the optical equivalent of turning up the volume on a speaker when no music is playing. You may amplify static, but you cannot create a missing song. To navigate the blackness, the technology must act as a hunter, searching for tiny, invisible fragments of information hiding in the shadows. These devices function as translators, converting unseen physical signals into a visual language the human brain can process. Across open terrain, the primary challenge for any night vision system is gathering whatever faint, natural light is already present. Passive analog systems rely entirely on ambient traces, like starlight or sky glow, to construct images covertly. In windowless rooms or absolute indoor darkness, these ambient traces vanish and passive systems fail. Digital systems solve this by using an active infrared illuminator. It acts as an invisible flashlight, flooding the scene with near-infrared energy. This creates a tactical risk. To anyone else equipped with night vision, that illuminator shines like a beacon. Environmental obstacles like heavy fog present a different problem, physically blocking infrared light from penetrating. Thermal imaging abandons reflected light entirely. Instead, it maps the environment by detecting which objects are emitting more heat than their surroundings. Thermal bypasses total darkness and camouflage, but it provides less detail for reading fine textures, writing, or the edges of ordinary glass. Fusion systems address these limitations by layering both technologies together simultaneously. This merges the detailed structural geometry of intensified light with the immediate threat detection of heat signatures. Once caught, the device must process that data to make it coherent for the user. A high-resolution screen is effectively useless if the underlying sensor cannot gather enough light to form a clean initial image. The struggle to find scarce light introduces random electronic variations. In the final image, this appears as a chaotic grain or snowy texture. Light intensity spikes when a sudden bright source hits the sensor, overloading the system. Modern devices use automatic gain control to counter this. A secondary curve immediately caps the peak, electronically throttling sensitivity in milliseconds. A high-end device relentlessly filters this environmental chaos, shielding the eye from blinding bursts while preserving the faint details of the shadows. Even with advanced processing, the technology is limited by the physical and cognitive capacity of the human user. The hardware inherently reduces peripheral vision, forcing the operator into a restrictive tunnel vision perspective. Depth perception is also compromised. Because distances are harder to judge, ordinary features like stairs and low branches become significant physical hazards. Camouflage also behaves differently. Materials that blend into a forest during the day can reflect near-infrared light in ways that break standard visual rules. A uniform designed for daytime stealth can flash bright white under infrared illumination, making the wearer stand out starkly against the dark background. Because the technology alters the basic rules of vision, extensive training is required to teach the brain how to navigate this translated reality. These machines are catching tiny fragments of light that have traveled from the stars, the moon, or distant lamps. Night vision reveals the world you were already standing in, amplifying the traces of light that were hiding in the darkness all along.